Okay, guys, here's our first lecture for Unit 6, which is going to be about gravity and oscillatory motion. So let's get right down to it. Here is here is one planet, and here is another massive object. It is a smaller massive object. It is out there around the planet. It has a mass m2. We're going to call this one mass of m1, and it is traveling with a velocity. Okay, going that direction. And because these are massive objects, they exert a force on each other, because anytime you have a force, there is an equal and opposite force. If one object is exerting a force on another, the other is exerting a force on the first. This is always how it happens, according to Newton. Oh yeah, who came up with the law of gravity? And his big contribution in this was that he was really the first person to say that he was the first person to relate that what was going on in the heavens was the same thing that was going on here on Earth. Okay, if this guy watches an apple fall from the tree, and he actually put in his notes, in the margins of his notes that he was taking when he was writing the Principia Mathematica, that the reason that the moon goes around the Earth is no different than the reason why the apple falls from the tree. And I think I captured how he said it. It was really very eloquent, the way that he said it. And this actually led to a little bit of a history here. It's actually led to a lot of consternation, because in doing this, he brought the heavens down to Earth. A lot of people were afraid that Newton was disproving God, and this was a very worrisome thing for a lot of people. Although Isaac Newton was a very, very devout Anglican believer. There was no attempt to disprove God whatsoever. It was just, he just used the term heavens, and that sort of got people riled up. But this object, we know that this object falls at, well, we'll get to there in a minute. Well, here's what he asserted. Here's our mass one. It's experiencing a force in this direction, and here's mass 2, and it's experiencing a force right back in this direction. And in between them, we have this radius right here that goes from, we'll call it R. This radius goes from the center of one to the center of the other. I didn't quite draw that perfectly right here, but it would go to the center of the other object. And what he found was that if we increased one of these masses, that it would cause an increase in the force. And if we increased the other one of the masses, it would also cause an increase of the force. And so he asserted that the force of gravity between these two objects would be proportional to both m1 and m2, that if one increased, the other one increased. So both of those would work. But then also that as the distance increased or decreased, the force would also change. However, the distance would have a larger effect. The change in distance would have a larger effect on the actual gravity. So if our radius increased, if our radius doubled out to here, then the force of gravity for the same masses would actually decrease by a factor of 4. Or if we were to bring this object in halfway and reduce the radius to half of what it was before, then all of a sudden our force of gravity would quadruple. It would be increased by a factor of 4. So we also discovered that it was an inverse square. It was proportional to the inverse of the square. That is, as the distance decreased, then the force increased. So that would be, they gave us a square down here. Okay, then the other thing was it would create if the radius was this way, so if we have the center of the circle here and the radius is pointing out, the force would act in the opposite direction. And we've had a discussion with this before. If it is towards the center, okay, then this becomes a negative r hat is the direction of this force, which winds up with, okay, that this is what our force is proportional to. Now, now he didn't know how to come up with this particular value, that there was a constant of proportionality for all of these things that is universal, that is the same throughout the universe. He didn't know what that was. But he did have the gall to call it big G. And this is now referred to as the universal gravitational constant. It is the universal gravitational constant, and it winds up at once. A guy named Henry Cavendish did an amazingly and elegant experiment to measure this actually very closely. That G winds up being 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, and these units are just there to cancel the kilogram squared to cancel with the two masses, and the meter squared to cancel with the radius squared. So that's why we have these units. And this was it. This was the law of gravity. This is what we had until about 1915. This lasted for 250 years, until about 1915, when Einstein came up with his general theory of relativity, and that really complicated things, and the math involved in that involves tensor calculus and some pretty hardcore stuff that I don't even know, because I bailed out on my physics major before I got to that particular point. But it's some pretty heavy stuff, and that's that's for really massive scale stuff, or things that are moving really fast. However, we do not need special relativity or general relativity. However, to say go to the moon, we do just fine with Newton's laws. In fact, that's all they really use. That's all that that's all that the Apollo program needed in order to get up there. In fact, there's a really cool program, a game right now called the Kerbal Space Program, that if you're interested in orbital dynamics and gravity and how the heavenly bodies work, that's a really cool program to pick up. Now, I do want to tell you guys that G represents a very, very weak force. And to illustrate that, let's say we have 1 kilogram, a 1 kilogram mass here that's hanging, and it's in proximity, relative proximity to another kilogram. Okay, both of these are 1 kilogram, and believe it or not, they are exerting a force on each other. And the distance between the centers of each of them is 1 meter. And we want to determine the force of gravity between these guys. Well, let's see how difficult this is to do. The force of gravity is going to equal this G times 1 kilogram times the other kilogram divided by 1 meter squared. So if we take two mass of 2 kilograms and we hold them a meter apart, okay, we can plug that into the equation here, and we're left with G. So the force of gravity then would equal 6.67 times 10 to the negative 11th newtons, or 66.7 piconewtons. Okay, because if I move the decimal back, that makes this a 12. 66.7 piconewtons, which is an exceedingly small number. Okay, really, really, really small. Now, what I do want to address now is we're going to talk a bit about acceleration due to gravity, and further address how we were able to show that an object close to the Earth is actually doing the same sort of thing. So here is what Newton was able to do, and this is actually pretty remarkable. So we're going to move this. We're going to move this over here. That we're on this moon, or that we're on the planet, and we're able to measure that on the planet the apple is going to fall with an acceleration equal to 9.8 meters per second squared. Well, we know that look at it like this. Our g, if we were to solve for g, this equals the force of gravity times the radius squared divided by the two masses. Okay, and if we wanted to compare the accelerations due to gravity of both of say the moon. Okay, if someone's up here on the moon, it's experiencing this as its centripetal force, and then our apple is falling to the ground. If we want to compare their accelerations, we're going to get the acceleration of the moon divided by gravity is going to, okay, all of these other things are equal, okay, except we get for the moon, right, we get 1 over the radius of the moon, so the orbit, the radius of the orbit from the center of the Earth out to the moon, okay, divided by 1 over the radius of the Earth. Okay, because really, holding an apple off the tree, that extra 2 meters, 3 meters, isn't going to affect the distance from the center of the Earth. Okay, and this equals, I'm sorry, and both of those are squared. So 1 over rm squared over 1 over re squared. You flip on which one's on top. So re squared equals radius of the moon's orbit squared. And this one, now they were able to calculate both of these. Okay, and this winds up being that the radius of the Earth is 6.37 times 10 to the 6th meters squared over 3.84 times 10 to the 8th meters squared. And I happened to figure this out ahead of time, that this equals 2.75 times 10 to the negative 4th is the ratio of the acceleration of the moon to the acceleration due to gravity near the surface of the Earth. So they could actually tell how far the moon was falling just because they didn't need to know g. They could figure it out using this ratio. Okay? But we can figure it out because we know that the acceleration, that g, acceleration due to gravity, equals 9.8 meters per second squared. So that's the acceleration of gravity, but we also know that the acceleration of the moon is equal to the velocity of the moon, okay, divided by the radius of the moon, because that's what is keeping the moon traveling around the Earth. It is traveling in the circle around the Earth, and it's, now mind you, it doesn't have a circular orbit; it has an elliptical orbit. We're going to get to that in a couple days. But the idea is that it's close enough to be circular. So this v squared over Rm. Okay, if we divide that by 9.8 meters per second squared, we can start figuring out what our, and this whole thing is going to equal the 2.75 times 10 to the negative fourth, so we can start figuring out what our velocity is. Well, our velocity, the way we figured it out, you know, we know that it's 2 pi radius over the time it takes to go for one full rotation, and they're able to figure out the distance it is to the moon. Or this is how they were able to figure out the distance it is to the moon, because they could figure out how fast it was going. All right, so we plug this in, we get AM equals 2.75 times 10 to the negative fourth meters per second times 9.8 meters per second squared. That's going to equal 2.70 times 10 to the third, negative third, meters per second squared. This does not have units right here. My mistake. That should not have units, because that's the proportion. All right, but then we know that AM is, you know, this part right here, so we're going to start plugging that in, and we're going to get 2 pi r squared over the time, over the period, the time it takes to circle the Earth, divided by r. Okay, and we're able to find that, you know, that this 2 pi, I'm sorry, this 4 pi r over, I'm sorry, this whole thing should be squared. Shoot, parentheses 2. This whole thing should be squared. This r cancels into there, so that's 4 pi squared r over t squared equals 2.70 times 10 to the negative third meters per second squared. And from here we can start figuring out, and we know what the t is, so we know that, so we can figure out from here what the radius is. And that's how we can figure out how far it is away from the Earth. Now, Henry Cavendish, and I'm going to do this down at the bottom of this page because this is, just kind of use this bottom space right here. Henry Cavendish measured G in 1798, and with just an absolutely elegant experiment, and it blows my mind that he did this. He mounted on a very long wire from the ceiling a very thin rod with a couple of masses on either side. Okay. On this rod, he had a mirror. Okay. He had this mirror on the rod. And at the other side of the room, it was a very dark room, and on the other side of the room, he had a window. Okay, with a thin slit in the window. And through this slit, he allowed light in to hit this slit, and it would bounce off, and so lower down on the wall, then he had a board where he could mark where the light would bounce to off of this mirror. Okay, so the light would go and would bounce off, and it would come back here. Let's see if I can use a darker yellow to illustrate this. So then he put two massive spheres on either side of the rod. Okay, they were the same distance. knew exactly how far they were. He knew how far this rod was. Okay, and this whole room, this whole room was darkened, and it was enclosed, and no wind was allowed to draft. And then when that happened, this is what he found, was that the light from this window would come in, and the mirror would turn just a little bit. Oh, I lost some. The mirror would turn just a little bit. And because it would turn, it would change where on his reflecting paper the light hit. And because he had these distances, and he had all of this all measured out, he would be able to measure the torque on the rod based on how far and over what time that this was able to turn. And through that, he was able to calculate that G equaled 7 times 10 to the negative 11th Newton meters squared per kilogram squared. This is a remarkably ingenious experiment based on how far the light was and what the angle was and created angular rotation. Just a genius experiment. And that's how we discovered what G was. Okay, now from this we were able to discover what the mass of the Earth was, because then all of a sudden we know that the force of gravity on an object equals G m, little m, over the radius of the Earth squared. Well, if we're trying to look for big M, then this becomes m equals radius of the Earth squared times the force of gravity over little m G, and we wind up that the mass of the Earth equals 5.98 times 10 to the 24th kilograms, which is the actual value. And that's Newton's law of gravity. That's how he did it. But the big thing is, here's our equation. There's a whole other mind-blowing thing that's going to come up, because this equation looks very much like another one that we're going to see in just a short time. And yes, there are parallels, and no, it's not the ones that you think, and no, there's another question that always comes up when we talk about the new equation, and we'll have to dispel a couple myths. So that's it for gravity, and I'll get that assignment up there as soon as I can. We'll talk to you later.